So this is the beginning of our second video for radioactivity and nuclear chemistry. In the previous video, we had looked at the discovery of radioactivity and the different types of radioactivity. And then in this next video, we're going to be looking at the valley of stability and how we can predict the types of radioactivity that occur, also how to detect the radioactivity, and then the kinetics associated with that radioactive decay, and also radiometric dating. So I want to ask the question, what causes a nuclei to break down? The particles in the nucleus are held together by a very strong attractive force only found in the nucleus called the strong force. And those only act over a very short distance, those strong forces. So the things, the nucleons, the things that are in the nucleus of the atom, so the neutrons and the protons are held together by this strong force. And the neutrons are very important because they play an important role in stabilizing the nucleus, because they add to the strong force. They have this stickiness that helps hold the nucleus together. But unlike the protons, they don't repel each other. Because remember, the protons have positive charges, and so the like charges are going to repel each other. So having the neutrons in there helps stabilize that nucleus because it contributes to the strong force. So as we start looking at the strong force and what causes a nuclei to break down, we want to first examine the neutron to proton ratio. So that's this N to Z ratio, where N represents the number of neutrons. Let me pull up my pen. So N is the number of neutrons, and Z is the number of protons. And this ratio is very important to measure the stability of the nucleus. If that ratio is too high, then the neutrons are converted to protons via beta decay. So if that N to Z ratio is too big, what we can do is undergo a beta decay. And remember that beta decay is when a neutron gets converted to a proton. So if the neutron gets converted to a proton, the N value goes down, the Z goes up, and so that's going to bring the ratio down to a smaller number. So if it starts off too high and you undergo a beta decay, so remember that's converting a neutron to a proton, you can lower this ratio. But if the N to Z ratio is too low, you can convert the protons to neutron by either positron emission or electron capture. Now this can also happen by alpha decay, but it's not as efficient, so we're only going to focus on either positron emission or electron capture. So this magic ratio of the neutron to protons that give it special stability, because sometimes it may be too high, sometimes it may be too low, but then there's that just right. So this is why we have that picture of Goldilocks. So once you achieve the optimal ratio, then your nucleus is more likely to be stable. So here we have a graph that's showing the number of neutrons versus the number of protons for different elements. And these green dots here are all stable isotopes. And so these green dots represent what we call the valley of stability. So these are the isotopes that are stable and aren't going to experience radioactive decay. Now if you'll notice at the beginning of this graph, if we're talking about from 1 to 20, so in this area here, notice how the slope of this line is very close, basically 1. So for elements with atomic numbers 1 through 20, the ratio that's optimal for them is a ratio of 1. So basically the same number of neutrons as the same number of protons. But as you increase the number of protons, notice how this kind of has this a little bit of a curve upward, and we start to deviate from this linear line. So when that happens, for atoms with number of protons from 20 to 40, the ratio that's optimal for those elements is 1.25. And as you increase the number of protons, so 40 to 80, that N to Z ratio approaches 1.5. So the more protons that are there, the more neutrons are going to be needed to stabilize that isotope. So we have to have a larger N to Z ratio. Now, if we're talking about atomic numbers greater than 83, so notice there's nothing stable, anything higher than 83. So there are no stable nuclei higher than 83. Now, what's really interesting about current research is that they're predicting that there's going to be another valley of stability out here somewhere. So that's why they're trying to synthesize these new elements. So they're hoping to find a new element that's stable and finding a new valley of stability, even though currently there are no isotopes that are stable in this area right here. So let's see how we can apply this information. So in this example problem, we want to determine the kind of radioactive decay that magnesium-22 undergoes. So remember, we want to compare that N to Z ratio and magnesium-22. So 22 represents the total number of neutrons and protons. And if I look at the periodic table, magnesium has 12 protons. So magnesium has 12 protons. Its atomic number is 12. So 22 minus the 12 gives me 10 neutrons. So that's the number of neutrons that are in this magnesium-22. And if I compare that N to Z ratio, 10 neutrons for every 12 protons, that ratio is 0.83. So that's less than 1, because we're looking for a stable nuclei of an N to Z ratio of 1. So if I want to get to a value of 1, an N to Z ratio of 1, I need to increase my number of neutrons and decrease my number of protons. So the type of radioactive decay that will do this will be either positron emission or electron capture. So since that magnesium-22 N to Z ratio is low, it should convert a proton to a neutron. So it can do this by positron emission or electron capture. Because remember, if we're starting off with magnesium-22, that's got 12 protons. If I convert that by positron emission, that will be converted to sodium, because sodium has 11 protons. So notice that the sodium here has an N to Z ratio of 1, because there are 11 protons, so there are 11 neutrons for 11 protons. Because remember, I find this number of neutrons by taking the 22 minus the 11. Now besides the N to Z ratio, the actual number of protons and neutrons affect the stability. And most stable nuclei have even numbers of protons and neutrons, and only a few have odd numbers of protons and neutrons. So if the total number of nucleons adds to a magic number, the nucleus is more stable. So this is the same idea as the electrons in the noble gas, resulting in more stable electron configuration. So remember, if we look at helium, helium has the 1s orbital completely filled, so it has 2 electrons. And if we consider neon, neon has the s and the p orbitals filled, so it has 10 electrons, and then argon has 18, krypton has 36, xenon has 54, and radon has 86. So those contribute to a stable noble gas configuration, and those elements weren't very reactive. That same idea of quantum numbers for the electrons can also apply to the nucleons in the nucleus. So a nucleus is most stable when either the number of neutrons or protons equal 2, 8, 20, 28, 50, 82, or 126. So these are what we call the magic numbers. Now these magic numbers we're not going to ask you to memorize, but we just want you to know that they exist and why they exist. So let's just compare this data of the number of stable nuclides with even and odd numbers of nucleons. So if we have even numbers of protons and even number of neutrons, notice that number of nuclides, there are 157 nuclides that are stable if they have even number of protons and even number of neutrons. If we have an even number of protons and an odd number of neutrons, there are 53 stable nuclides. And if we have an odd proton and even number of neutron, there are 50 nuclides. But notice if both of these numbers are odd, there are only 5 nuclides that are stable. So having odd numbers of protons and neutrons doesn't contribute to the stability. So if you want a very stable nuclide, you want an even number of protons and an even number of neutrons. And if you want to be even extra stable, then you want one of these magic numbers of 2, 8, 20, 28, 50, or 82, or 126. Now next we want to look at detecting radioactivity. So to detect something, you need to identify what it does. And remember when we talked about the discovery of the uranic rays, how these elements or these minerals were wrapped in photographic paper and they caused the photographic paper to be developed even if they were hidden in a drawer or wrapped up in something so that light couldn't shine through it, but the radioactive material caused the photographic film to be exposed. So this same idea is what's used in these badges here. These film badges, you'll sometimes see some of the technicians that do some of the nuclear medicine tests at a hospital, or maybe if you're looking at a research facility. I was actually doing research at the National Lab in Oak Ridge, Tennessee, and I actually had to wear one of these badges. And at the end of my term there, they collected my badge to see how much radiation I was actually exposed to. So notice that inside this plastic box, it's completely sealed so that light can't interact with that photographic film. But any kind of radioactivity can penetrate the plastic here, and so they can look to see how much radiation you're exposed to by how much that film is developed over a certain period of time. Now, when you're detecting radioactivity, those radioactive rays cause air to become ionized, so they become charged. And an electroscope, we saw that in that first video, detects radiation by its ability to penetrate the flask and ionize the air inside. Now, a Geiger counter works by counting electrons generated when argon gas atoms are ionized by radioactive rays. So you've probably seen this in some TV shows or seen maybe in another lab, but you have this little box here and it looks like a little microphone here, and you hear these clicking noise, and the clicking noise and how fast it clicks represents the number of radioactive particles that are seen or detected by the Geiger counter. And the way this works, you have this tube here and it's filled with argon atoms. And you've got a thin window here, and the particles, the radioactive particles, can pass through this thin window. And as it passes through and collides with the argon atoms, they become ionized. So the argon atoms become positively charged and they eject an electron. And that electron is then attracted to the positively charged anode, and that completes the circuit. And you have a detector here that counts the number of ions that hit the anode. And so that's what that clicking noise that you hear is from. So the more clicks that you hear, the more radioactive particles that are being detected by the Geiger counter. Now, radioactivity is just a natural part of life. There are small amounts of radioactive minerals in the air, ground, and water, and even in the food you eat. So what's really interesting, if you were to take a Geiger counter to a banana, bananas have potassium in there, and there's a particular isotope of potassium that's radioactive. So you can actually hear clicking noises if you were to hold a Geiger counter up to some bananas. Now, the radiation you are exposed to from these natural sources, that's called background radiation. And as we're looking at radioactivity, it was discovered that the rate of change in the amount of radioactivity was constant, but different for each radioactive isotope. And the change in radioactivity was measured with Geiger counters, and they're measured in counts per minute, so that clicking noise per unit of time. And each radionuclide had a particular length of time that it required to lose half of its radioactivity. So they had constant half-lives. So remember, the half-life is the amount of time that it takes for half of the material to decay or be consumed. And what we know from when we study kinetics is that processes that have constant half-life follow first-order kinetic rate laws. So all of the reactions that we look at when we're talking about radioactivity all are going to be first-order kinetics. Now, another interesting thing that they learned when studying the rates of reactions of radioactive material is that they learned that the rate of change was not affected by temperature. So if temperature does not affect the rate of the reaction, that means that radioactivity is not a type of chemical reaction. Now, just to kind of review as we look at the kinetics of radioactive decay, remember we said that radioactive decay is always first order. And here we're just writing the rate law expression here where the rate equals a constant times the concentration. And rather than looking at concentration like molarity like we did when we looked at the kinetics chapter, we're going to have N, and that's just the number of radioactive nuclei. And since this is a first order reaction, the half-life equation is going to be equal to T1/2 equals 0.693 divided by K, so that the rate constant for the reaction. And the shorter the half-life, the more nuclei decay every second. So we say that the sample is hotter. Sometimes you may hear of an area that's contaminated with nuclear material. They say it's a hot zone or a hot area. So the more nuclei that are decaying per unit of time, the hotter the sample is and the hotter the area is. Now, just a reminder, remember you're going to be given the integrated rate laws on your reaction sheet for any exams. And on your sheet, we have the Ln of the concentration of A equals negative KT plus the Ln of the initial concentration. So that would be given to you on your cover sheet. Now I can rearrange this equation so that the Ln of A minus the Ln of A naught equals negative KT. And I can then combine this, so the Ln of the concentration of A over the concentration of A naught, that initial equation. So remember, this is the Ln of this entire ratio equals negative KT. And then rather than saying the Ln of the concentration of A over the initial concentration of A, remember with the nuclear reactions we're going to use the number of radioactive nuclei. So this is where this equation comes from. It's an integrated first law reaction. So the Ln of the number of radioactive nuclei at a particular time over the initial amount of radioactive nuclei equals the negative KT. And K is just our rate constant, and T is the time of the reaction. Now remember when they said that we're studying the radioactive reactions and they said that the half-lives were unique for the different isotopes? So I just want to give you an idea of some of the different types or the different lengths of the half-lives of various nuclides. So thorium-232 has a half-life of 10 to the 10th years, and it's going to undergo alpha decay. Uranium-238, 10 to the 9th years. Carbon-14, which you've probably seen in carbon dating, that's on the order of 5,730 years. So it takes 5,730 years for half of the carbon-14 to decay into a nitrogen isotope. And that's going to happen by beta decay. Now compare that to radon. So radon is a gas, and it's formed by the process of uranium decaying, and that's basically a minute. So for every minute, half of the radon is going to decompose, and that's to undergo alpha decay. Now compare that to thorium, which has a very quick half-life, 10 to the minus 6 seconds. So we're talking about microseconds for half of the thorium to decay. So again, we're just emphasizing that the half-lives are unique to the type of the nuclide. So this really should be a review of some of the kinetics, but we're just applying it to a nuclear system. So on this graph, we're looking at atoms of radon-220. And remember we said that the radon had a half-life of approximately 1 minute. So we've got the atoms on the y-axis, we've got time on the x-axis. And notice that after a minute we go from 1 million to 500,000 to about 250,000. And each minute passes, we undergo another half-life. So another way of looking at the same information, rather than having atoms on the y-axis, here we've got percentage of the original sample. So we've got 100% at the beginning, and after the first half-life, we have 50%, divide that by 2, and that's 25, and then 12.5, and each time we go through a half-life, we're dividing that amount by 2. So remember, half the radioactive atoms decay each half-life. So if we're looking at the decay of radon, so that's that graph that we're looking at a couple of slides ago. This is an EPA map of radon zones. Now radon is a product of the decay of uranium. So uranium will decompose to make radon. And radon is a gas. Remember, that's one of the noble gases. So what happens is that if you are to breathe the radon in, it gets trapped in the lungs. And remember, this is an alpha emitter, and when it's inside the lungs, it's going to increase your risk for lung cancer. So if you move to any of these parts of the U.S., you have to be careful about the home that you buy, particularly in the Midwest. So a lot of these homes have basements, and on the East Coast and the North here, a lot of these homes have basements. And radon is a very heavy gas. So a lot of times you have to worry about radon seeping into the basement and not being circulated out, and the air being freshened so that radon can actually pool in the basement. And people can have high levels of radon in their house. And sometimes people have trouble selling their house because they can't get rid of the radon. And in these areas where they have high amounts of radon, there's usually uranium in the soil, and the uranium is decomposing to give the radon, and then that gas then seeps to the lower levels because it is very dense. So be careful if you move to any of these areas to make sure you don't buy a home that has high radon levels. Now let's look and see how we can apply some of these kinetic problems. So in this example problem, we have 1.35 milligram sample of plutonium-236, and they want us to calculate the mass that will remain after 5 years. So we're given the mass of the plutonium, so it's at 1.35 milligrams. The timeline that we're looking at is 5 years, and the half-life, we can look that up on a chart, and the half-life of that is 2.86 years. So we want to find the mass in milligrams, that's left after that 5-year period. So using the half-life, we can calculate the rate constant. And then we can use the rate constant, the initial mass, and the time, and we can find out the remaining mass. So what's going to allow us to do that, remember this is the half-life expression, so if we know the half-life, we can solve for K to get the rate constant. Then once we have the rate constant, we can substitute in the equation here for that integrated rate law expression. And we know the initial amount, so the N naught. We know the K because we solved for it here. And we're given the time period of 5 years. So then we can solve for the NT. So this is the remaining amount of sample after 5 years. Okay, so again, substituting into the half-life equation, we find K. And that rate constant is 0.2423 inverse years. So that's our rate constant. So now that we know our rate constant, we can substitute into our integrated rate law. So here, to get rid of the ln, I'm going to raise both sides of the equation. So e raised to the ln of nt over n0 and e raised to the negative kt. So when that happens, that gets rid of this portion. So that nt over n0 equals e raised to the negative kt. Then if I multiply both sides by n naught, So the N naught cancels out, and that way NT equals the N naught times E raised to the negative KT. So we said that N naught, this is the initial amount of nuclide, so we have 1.35 milligrams. E is the natural number E, and negative of the K, so that K value we found previously, so that 0.2423 inverse years. And time is 5 years, so notice that the years will cancel each other out. And so the NT equals 0.402 milligrams. So the units are correct, and the magnitude makes sense since it's less than 1/2 the original mass, and for longer than 1 half-life, so that makes sense to us. So after 5 years, that 1.35 milligram sample of plutonium-236, there will only be 0.402 milligrams left. Now that we've looked at some of the kinetics associated with radioactive reactions, we can look at dating objects. And if it's a mineral that we're looking at, so we're looking at geological material, we can compare the amount of uranium-238 to lead-206, or we can compare the amount of potassium-40 to argon-40. But if we want to look at something that was once living, so if we're talking about archaeological samples, we can compare the amount of carbon-14. So we can compare the carbon-14 to carbon-12 ratio. And if you'll recall, we said that the carbon-14 radioactive half-life is 5,730 years. So when a substance is living, the ratio of carbon-14 to carbon-12 is pretty much consistent. It's going to be about the same no matter what point in the life of the living thing. So we're talking about grass or a person or an animal, such as a deer or something like that. But the ratio of carbon-14 to carbon-12 is fairly constant. Because, let's see, the CO2 in the air is the ultimate source of carbon in an organism. And the atmospheric chemistry keeps producing carbon-14 at a nearly constant rate that it decays. So it's balancing each other out. But once something dies, it's not intaking more carbon. So what happens is that the carbon-14 to carbon-12 ratio decreases because you're not uptaking more carbon. So the carbon-14, you're not increasing that source. That carbon-14 starts to decay, and you have less carbon-14 for every carbon-12. Now when we're using carbon dating, the limit is about 50,000 years. You may hear different sources, 50 to 60,000 years, but that's about the upper limit of the amount of time that you can measure with carbon dating. Because mainly when after about 50,000 years, you're really reaching some of the detection limits of the instruments that detect the carbon. So you've got some error in the measurement. So 50,000 years is the limit that we can look at for carbon dating. So here's just a graph to kind of look at. So if we're looking at the percent carbon-14 relative to a living organism, so basically, as soon as you're dying, you're about what you were when you're living, so 100%. And say this organism dies. Well, after the first half-life, after 5,730 years, you're only going to have 50% of the carbon-14. And then after another 5,730 years, so a total of 11,460, you're going to have 25% left. And so each time you're decreasing the carbon-14 by half, so because we're going through these half-lives. So after 6 half-lives is a time period of 34,380 years. So let's think about if we had an ancient artifact that we want to look at. So what happens is, remember, the carbon-14 is relatively constant. So let's go ahead and write the equation for carbon-14. And carbon has 6 protons in the nucleus. And notice that that N to Z ratio is 8/6. So that's the same thing as 1.3. So that ratio is too high because remember we want a ratio of approximately 1:1. So we want that ratio to be about 1. So what's going to happen is that the carbon is going to undergo beta decay. So the carbon-14, So carbon-14 is going to undergo beta decay, and when it does that, that creates nitrogen-14. So nitrogen has 7 protons in the nucleus, so that one of those neutrons is converted into a proton when we have that beta decay. So we go from carbon-14 to nitrogen-14 as we emit that beta particle. So let's say we found an ancient artifact. We measure the amount of carbon-14 in it, and it's about 12%. Well, then we can figure out that that artifact is about 17,000 years old. So that's how carbon dating works. Now, what you'll find on Blackboard is a video that kind of walks you through some of the same ideas as we discuss here. So they're just showing you an ancient artifact that you're just trying to figure the age of it. And you can measure the carbon-14 in that by doing a carbon-14 analysis. So that carbon-14, the nuclei ratio is 8 neutrons to 6 protons. It gives you a ratio of 1.3. And then as you undergo beta decay, so you eject that electron from the nucleus, or that electron type particle, converts it from carbon-14 to nitrogen-14. So after 5,730 years, that's the first half-life, 50% of the carbon-14 remains. And then with each half-life, we're starting to decrease the amount of carbon-14. So in this artifact, they're showing us that it has a 12% carbon-14. So knowing that it's 12% carbon-14, we can figure out that that item is about 17,000 years old. And this is just a plot of looking at the remaining carbon-14 and how it decays in that logarithmic scale. So this is the end of our second video. You will find the next video, and in that next video we're going to look at how nuclear chemistry relates to energy and the discovery of fission and nuclear fusion. And we'll also look at how radiation is used to benefit life, so looking at how radioactivity is used in medicine and other applications.